Have you ever stared up at the night sky and wondered what's really out there? Not the stars, not the planets, but the unknown, the places where light itself vanishes, where time breaks down, where the rules of reality collapse into something terrifyingly different. Black holes are not just cosmic objects, they are nature's ultimate paradox, the deepest secrets of the universe, and the closest thing we have to real-life nightmares. And yet, they might also be the key to understanding everything. Tonight, as you close your eyes and drift into sleep, prepare to journey through the most mind-bending black hole theories ever proposed, the ones that question the very fabric of reality. What happens when you cross the event horizon? Does time stop? Does it stretch infinitely? Could black holes be gateways to other universes? And the biggest question of all, could black holes one day consume everything, including the universe itself? But here's the most chilling part. Black holes aren't just far-off cosmic monsters. Right now, as you're lying here, somewhere in the vast emptiness of space, a black hole is silently devouring entire stars, crushing planets like dust, bending time and light in ways we cannot yet understand. Some are wandering, unseen, moving through the galaxy like cosmic assassins, and one day, perhaps sooner than we think, a black hole could come for us. Even Stephen Hawking once warned, black holes are not just holes, they are traps for reality itself. So, are you ready? Ready to uncover the most chilling theories ever conceived about these cosmic nightmares? Ready to feel your mind expand and maybe never see the universe the same way again? Then let's begin. Everything you know, everything you've ever touched, seen, or felt exists because the universe obeys rules. Rules of physics, space, and time that hold everything together. But what if there was a place where those rules cease to exist? A place where time no longer moves forward, where space collapses into nothing, and where everything, matter, energy, information, gets swallowed by an impossible abyss. That place exists. It is called the singularity. Deep within the heart of a black hole, beyond the event horizon where nothing can escape, lies a region so extreme that it breaks the very foundation of reality. Scientists have tried to define it, to calculate its nature, but every attempt leads to contradictions, infinities, and a dead end in physics itself. Even Einstein's theories, which describe the warping of spacetime with stunning accuracy, crumble when applied to the singularity. But what is it, really? Is it a place, a moment, a state of existence beyond human comprehension? Or is it something else entirely, something that reveals a secret about the universe we were never meant to know? The singularity is more than just the core of a black hole. It is the ultimate unknown, and if we ever truly understand it, we may finally uncover what reality is made of, what time really is, and how the universe itself will end. At the center of every black hole, there exists a point of no return, not just for matter or light, but for understanding itself. It is called a singularity because it is, by definition, singular, a place where all known laws of physics break down, where gravity becomes infinitely strong, and where density reaches an impossible limit. Density in the universe as we know it follows certain rules. Stars, planets, and even neutron stars are made of atoms, packed together under pressure. But there is a limit to how dense something can be before it collapses under its own weight. In the case of a black hole, that limit is obliterated. Inside the singularity, density is infinite. That means that all the mass of a collapsing star, or anything else that falls into the black hole, is crushed into a single point with zero volume. A place where the concept of size no longer makes sense. But infinite density is more than just a bizarre concept. It is a red flag in physics. Every time equations spit out infinity as an answer, It signals that something fundamental is missing from our understanding. The singularity is not just an extreme version of something familiar, it is an entirely different category of existence, one that science has not yet found a way to explain. And the effects of this mystery don't just stay hidden inside black holes. They ripple outward, challenging everything we thought we knew about the universe. If singularities exist, then the universe itself may have begun as one, a single point of infinite density that exploded into everything we see today. This is where space and time itself start to fall apart. The universe operates under the assumption that space and time are connected, forming what scientists call the fabric of space-time. But at the singularity, that fabric is ripped apart. Time no longer flows. Space ceases to exist as we understand it. Everything collapses into a realm beyond physics. Even the strongest forces we know, gravity, electromagnetism, and the nuclear forces that hold atoms together, become meaningless inside the singularity. The very forces that shape the cosmos are shattered, leaving behind a place that defies all comprehension. Some scientists believe that this means the singularity is not a place at all. Instead, it may be a flaw in our equations, a sign that we need a new theory, one that merges quantum mechanics with Einstein's relativity, because as of now, the singularity represents a crack in reality itself, a cosmic glitch that refuses to be solved. But here's where things get even more unsettling. If the singularity is truly a place of infinite gravity, then anything that falls into a black hole is stretched, torn apart, and ultimately crushed into non-existence. That includes light, matter, and even entire stars. But what happens to information? Does it simply vanish from the universe? This question is one of the biggest mysteries in physics, and it leads to an even deeper paradox, because according to the fundamental laws of quantum mechanics, information cannot be destroyed. It can be transformed, hidden, or scrambled beyond recognition, but it must always exist in some form. But inside the singularity, that rule might be broken. If information truly disappears inside a black hole, then our entire understanding of physics would have to be rewritten from the ground up. Some scientists believe that information is somehow stored on the event horizon, like a hologram, encoded in ways we have yet to understand. Others suggest that the singularity itself is not the end, but a doorway to somewhere else. This leads to an even more chilling possibility. If space and time collapse inside the singularity, then what happens when a black hole dies? If Hawking radiation eventually causes black holes to evaporate over trillions of years, does the singularity inside cease to exist? Does it release all the trapped information? Or does it tear a hole in the universe itself? Some theories suggest that instead of disappearing, singularities could give birth to new universes. If the singularity is not an end point, but a beginning, then every black hole could be a seed for a new reality, each with its own laws of physics, its own version of space and time. This would mean that black holes are not just cosmic monsters that destroy everything they touch. They may be the creators of new worlds, hidden from our view, locked behind the event horizon. And if that's the case, then perhaps our own universe began inside a black hole too, a singularity that expanded, against all odds, into the reality we now call home. But this idea leads to yet another disturbing question. If singularities can birth new universes, then where is the black hole that created ours? If our universe was once a singularity inside some larger, unknown cosmos, then what lies beyond it? Are we trapped inside someone else's black hole, part of a chain of realities stretching infinitely into the past and future? We may never know, because the singularity is not just a place beyond our reach. It is a place beyond our understanding, a place where existence itself collapses into a mystery so deep that it may never be solved. And yet, black holes continue to pull matter, energy, and even light into their depths, feeding their singularities, growing larger and more powerful as the universe expands. Some are billions of times the mass of our sun, lurking at the centers of galaxies, devouring everything in their path. Others may be small, hidden, wandering the cosmos unseen. And if the theories are correct, some may even be waiting in the distant future to consume the universe itself. But the singularity is only the beginning of the horror. Because before anything can reach it, it must first cross the event horizon, the point of no return, where time warps, light bends, and reality itself begins to slip away. And once something crosses that threshold, it never comes back. The singularity is the final destination, the heart of a black hole where all known physics collapse. But before anything can reach that ultimate abyss, it must first pass a boundary that marks the true point of no return. It is the most feared edge in the universe, an invisible surface where time slows, space distorts, and reality begins to unravel. The event horizon is not a physical wall, yet it holds the power to trap even the fastest forces in existence. Light, the fastest traveler in the cosmos, cannot escape once it crosses this threshold. Beyond this point, escape is no longer a possibility, only an inevitable descent into the unknown. This is where everything changes. To an outside observer, an object falling toward the event horizon appears to slow down, its motion stretching infinitely as if frozen in place. The closer it gets, the more it appears to dim, fading into redder shades due to the immense gravitational pull warping its light. But from the perspective of the object itself, time flows normally. There is no sudden warning, no flashing sign announcing the crossing of this boundary. Instead, it falls forward without resistance, unaware that it has already left the universe as the outside world knows it. The event horizon is more than a boundary. It is a rupture in the structure of reality itself. It is where gravity grows so strong that escape velocity surpasses the speed of light. In normal space, no matter how powerful a rocket is, given enough energy, it can eventually break free of a planet's gravitational pull. But at the event horizon, even light, which moves at the highest speed allowed by physics, finds itself caught in an endless spiral, never to return. There is no force in the known universe capable of pulling anything back from this fate. The implications of such a boundary challenge every understanding of physics. In theory, if something crosses the event horizon, it should still exist inside the black hole, continuing its descent toward the singularity, but from the perspective of an outside observer, it never truly crosses. The intense gravitational pull stretches time near the horizon so much that an object falling inward appears to slow down infinitely. The closer it gets, the longer it takes for its last visible moment to reach an outside observer. To anyone watching, the object never actually falls inside. It only fades, redshifted beyond visibility, frozen on the very edge of existence. This creates one of the most unsettling paradoxes in modern physics. If an object can never be seen fully crossing into the black hole from an external viewpoint, does it truly disappear? Is it still there, just beyond the visible universe, or does it become something else entirely? The laws of relativity say one thing, but quantum mechanics, which governs the behavior of particles at the smallest scales, suggests another. According to quantum mechanics, information cannot be destroyed. It must be preserved in some form. But where does it go when it crosses the event horizon? Stephen Hawking's work on black holes suggested that they are not entirely black after all. Instead, they slowly emit radiation, a process now known as Hawking radiation. This means that, given enough time, black holes will eventually evaporate, disappearing into nothingness. But this raises another question. If the event horizon traps everything inside and nothing can escape, then how does Hawking radiation manage to leak out? And what happens to everything that has ever fallen in? Theories attempting to resolve this contradiction suggest that the event horizon is not just a simple boundary, but something far more complex. Some physicists propose that all the information that falls into a black hole is encoded on its event horizon, forming a kind of cosmic archive where everything that has ever crossed remains imprinted. This would mean that the surface of a black hole is not just a passive barrier, but an active recording of everything it has consumed. This idea, known as the holographic principle, suggests that the three-dimensional reality we experience might be nothing more than a projection of information stored on distant surfaces, much like how a hologram encodes a three-dimensional image on a two-dimensional surface. But what does this mean for anything unfortunate enough to cross the event horizon? While an outside observer would see it slow down indefinitely, the object itself would feel nothing unusual. It would continue its fall as if nothing had changed, experiencing no barrier, no sudden shift. But as it moves deeper inside, time warps in ways that defy human experience. The immense gravitational field distorts every moment, stretching time so that the journey to the singularity may feel like an instant or an eternity. As it falls, the surrounding universe would appear to speed up, racing forward at an accelerating pace. If the black hole has existed for billions of years, the traveler would witness the future of the universe unfolding in fast motion as they descend. This effect is due to gravitational time dilation. The closer something gets to the event horizon, the slower time moves relative to an outside observer. If someone were to hover just outside this boundary while watching the universe beyond, they would see time speeding up at an accelerating rate. In theory, a person suspended just outside the event horizon could witness the death of the universe itself, watching as galaxies burn out, stars collapse, and all of existence fades into darkness, all in the span of moments from their perspective. This strange warping of time also suggests an eerie possibility. If time slows infinitely at the event horizon, then in a sense, the black hole has already seen the end of the universe. From its perspective, it has existed through all of time, absorbing matter and energy, even from the distant future. This means that black holes, in some strange way, could be connected to the fate of the cosmos, existing outside the normal flow of time as we understand it. Some theories suggest that the event horizon itself may not be as smooth as general relativity predicts. Instead of being a silent boundary, it could be a chaotic, violent region filled with turbulence at the quantum level. This is the idea behind the concept of a firewall, a hypothetical layer of intense radiation that burns anything crossing the event horizon. If this were true, it would mean that anything falling in is instantly incinerated before it ever reaches the singularity. However, this idea conflicts with the smooth, seamless nature of spacetime predicted by relativity, making it one of the most debated questions in theoretical physics. There is also the question of whether event horizons are absolute. Some scientists propose that what we call a black hole might not be a permanent structure at all. If quantum effects allow for fluctuations in spacetime, the event horizon could be an illusion, a temporary boundary that eventually disappears. If this is the case, then nothing is ever truly trapped, only delayed, suspended in a kind of cosmic limbo until the black hole itself vanishes. For all its mysteries, the event horizon remains the ultimate dividing line between what can be known and what is forever lost. It is the cosmic edge where certainty ends, where the fabric of space-time stretches to its limits, and where reality bends in ways that may never be fully understood. To fall past this boundary is to surrender to forces beyond comprehension, to leave behind everything that was ever known and plunge into the depths of the unknown. And yet, black holes continue to grow, consuming everything in their reach. Some are small, formed from collapsed stars, while others, billions of times the mass of the Sun, anchor entire galaxies, influencing the motion of countless stars. These supermassive black holes shape the fate of the cosmos, determining the structure and evolution of the galaxies they inhabit. Every galaxy, including our own, has one at its core, a dark heart around which everything orbits. But where do these giants come from? How did they form, and what role do they play in the grand design of the universe? If event horizons are the borders of the unknown, then black holes themselves are the architects of cosmic transformation. They do not merely consume, they reshape, they distort, they dictate the fate of everything within their gravitational grasp. The event horizon is only the beginning of the journey inward, but its existence raises deeper questions about the fundamental nature of reality itself. If light cannot escape, if time slows infinitely, if information is both preserved and lost at once, then what truly lies beyond the edge? There is more to uncover, more to explore, because as terrifying as the event horizon is, what happens beyond it, the very forces that stretch and tear matter apart, may be even more disturbing. And for anything that falls beyond this invisible border, the nightmare is only just beginning. There is no coming back from the event horizon. Once an object crosses that invisible boundary, it is trapped forever, pulled toward the singularity by a force so immense that escape is no longer possible. But the journey inward is not a smooth descent. It is something far more violent, far more horrifying than simply falling into darkness. Before anything reaches the singularity, it undergoes a process so extreme that it stretches the very fabric of its existence, tearing it apart piece by piece, atom by atom. This process has a name that sounds almost humorous, yet it describes one of the most terrifying phenomena in the known universe. It is called spaghettification. The laws of physics, which govern everything from the movement of planets to the structure of the smallest particles, are built around forces of attraction and resistance. On Earth, gravity pulls everything toward the center of the planet, but other forces, such as the strength of molecular bonds, prevent objects from being crushed under their own weight. In space, gravity can be much weaker or vastly stronger, depending on where you are. Near a black hole, gravity is not just strong, it is overwhelming, an unstoppable force that dominates everything around it. And the closer an object gets to the singularity, the more extreme this force becomes. Spaghettification occurs because gravity is not equal on all sides of an object. When an object falls toward a black hole, the part of it that is closer experiences a stronger gravitational pull than the part that is farther away. If someone were falling feet first, the gravity pulling on their feet would be significantly stronger than the gravity pulling on their head. The difference in force would stretch their body apart, pulling them into an elongated shape, thinning them out like a strand of spaghetti. The effect does not stop at the body, it extends to every molecule, every atom, pulling apart even the fundamental structures that hold matter together. For a small black hole with a strong gravitational field, spaghettification happens quickly. The moment an object crosses the event horizon, the tidal forces, caused by the difference in gravitational pull between its near and far sides, become so extreme that no known material could withstand them. The object is stretched, then torn apart, its individual components following different paths toward the singularity. Each fragment experiences its own gravitational forces, stretching further and further until it is reduced to a stream of fundamental particles, spiraling inward in an unstoppable descent. For a larger, supermassive black hole, the experience of spaghettification is delayed. Because these black holes have much wider event horizons and their gravitational fields increase more gradually, an object may cross the event horizon without immediately being torn apart. In such cases, the person or object falling in would experience a longer descent, moving deeper into the black hole before reaching the point where the tidal forces become overwhelming. But this only postpones the inevitable. No matter how large or small the black hole, the fate remains the same. At some point, the gravitational pull becomes so uneven that no structure can hold together. The difference in force between one side and the other grows until it exceeds the strength of molecular bonds. The object stretches, thins, and ultimately disintegrates. At first glance, spaghettification may seem like an unusual effect caused by extreme gravity, but it is more than that. It is a direct consequence of the warping of space-time itself. When an object falls into a black hole, it is not simply moving downward as if pulled by a force. It is following a path through curved space-time. This path is not a straight line, but a stretched, accelerating fall into deeper and deeper distortions of space. The more space-time curves, the more elongated the path becomes. What looks like stretching and tearing is actually the natural way objects move in a region where gravity has reshaped the very nature of space. The process does not occur instantly. In the initial stages, the object is still intact, though it may feel an increasing sense of weight as gravity pulls harder on one side than the other. As it moves closer to the singularity, the stretching intensifies. If it were a spacecraft, it would begin to warp, its front end accelerating faster than the rear. Communications would distort, signals would be delayed or lost, as time itself is stretched along with space. As the effect grows stronger, the structure of the spacecraft would begin to fail. Metals, no matter how strong, would be pulled into thinner and thinner strands. If it were a human, bones would stretch, muscles would strain, and organs would shift, all while the person falling in would experience time moving normally from their perspective. The deeper the fall, the greater the forces become. Soon, not just the large structures, but the very bonds holding molecules together would snap. Chemical structures would unravel, the forces that bind atoms to one another would give way, and the object would dissolve into its most fundamental components. At this point, spaghettification is no longer just a stretching effect, it is complete disintegration. Atoms themselves, unable to resist the tidal forces, would be ripped apart, their individual particles sent spiraling toward the singularity. Even light, which normally travels in straight paths through space, is affected by the stretching of space-time near a black hole. If a beam of light were emitted just before an object reached its final moments of spaghettification, the light itself would be stretched into longer and longer wavelengths, becoming redder as it moved outward. This effect, known as gravitational redshift, means that to an outside observer, the final moments of an object falling in would appear stretched out in time, fading into the darkness as its light becomes undetectable. Inside the black hole, time and space function differently. From the perspective of the falling object, its descent would seem continuous. There would be no noticeable moment where it was torn apart. It would simply keep falling, moving faster and faster toward the singularity. But in reality, the spaghettification process would be unfolding relentlessly. Every fragment of the original object, every stretched molecule, every ripped-apart atom would continue its fall, following paths that converge ever more tightly toward the center. The strangest part of this process is that, from the point of view of physics, there is no well-defined final moment of spaghettification. The closer something gets to the singularity, the more space and time distort, making it impossible to determine an exact point at which it is destroyed. Instead, every particle, every fragment, continues an infinite descent, accelerating as space-time itself pulls them toward a place where physics no longer applies. This raises a disturbing question. If everything that falls into a black hole is stretched, torn apart, and reduced to fundamental particles, does anything of it remain? Is the information about what it once was lost forever? The paradox of black hole information loss remains one of the greatest mysteries in physics. If black holes destroy everything, does that mean the universe itself allows for complete erasure of history? Or is there some unknown mechanism preserving the traces of what was consumed? One theory suggests that information may not be lost, but instead scrambled and encoded on the event horizon. Another proposes that black holes could eventually leak their contents back into the universe through Hawking radiation, though in a form that may be unrecognizable. Others believe that the destruction caused by spaghettification is only part of a much larger process, one that leads not to total obliteration, but to something new, perhaps even another universe. For now, the only certainty is that black holes do not simply consume, they transform. What falls into them does not merely vanish, it is remade in ways that defy comprehension. The process of spaghettification is a glimpse into that transformation, a brutal demonstration of what happens when the forces of gravity grow unchecked. It is a reminder that there are places in the universe where destruction is not just an event, but a fundamental rule of existence. But black holes are not just destroyers. The matter they consume, the energy they pull in, does not always vanish entirely. In some cases, black holes give rise to something equally mysterious, something that might be their opposite, or perhaps their twin, a structure that, instead of devouring everything, repels it, sending matter and energy back into the cosmos in ways that seem impossible. There are theories suggesting that if black holes exist, then so too must their opposites, white holes. If black holes consume, white holes expel. And if they are connected, then the mysteries of black holes may not end in destruction, but in an escape into something entirely new. If black holes are the universe's most feared monsters, devouring everything that crosses their event horizon, then white holes, if they exist, are their paradoxical opposites. Instead of trapping matter, they repel it. Instead of consuming energy, they unleash it. The very idea that such objects could exist challenges the deepest assumptions about how space and time behave. They have never been observed, yet mathematics suggests they are possible, and their existence could be the missing piece to some of the biggest mysteries in the cosmos. White holes are more than just theoretical counterpoints to black holes. They force us to question everything we know about gravity, causality, and the nature of time itself. In a universe where everything is governed by interactions, where forces attract or repel, where matter is born and destroyed, white holes would be a contradiction that demands an explanation. They would be celestial objects that cannot form through any known process, yet must exist if the laws of physics are truly symmetrical. But if they are real, why have we never seen one? Could it be that they are hidden from view, appearing only under conditions we do not yet understand? Or could it be that black holes and white holes are not separate entities at all, but two sides of the same cosmic coin? The possibility that black holes and white holes are connected leads to an even deeper question. If black holes pull in everything and white holes push everything away, then what happens in between? What if these two extremes are not separate entities but different sides of the same phenomenon? If this is true, then black holes might not be the ultimate end for anything they consume. Instead, they could be cosmic gateways, tunnels through space-time leading somewhere else entirely. This idea brings us to one of the most tantalizing theories in modern physics, the concept of wormholes. The notion that black holes and white holes could be linked by a hidden structure in spacetime suggests that the universe might be more interconnected than previously thought. If such a bridge exists, it would mean that black holes are not just celestial traps, but portals to distant regions of the cosmos, or perhaps even to entirely different universes. Wormholes are among the most fascinating and controversial ideas in theoretical physics. The concept originates from Einstein's field equations, which describe how gravity shapes spacetime. In theory, spacetime is not a rigid, unchangeable structure, but something that can bend, twist, and even fold upon itself. If this is true, then distant points in space could be connected by shortcuts, tunnels through which matter and energy could travel instantaneously, bypassing the vast distances that separate galaxies and even entire universes. But for such a passage to exist, it would require an entrance and an exit, a black hole and a white hole connected by a corridor through space-time. If white holes truly exist, they might serve as the exit points for matter that has fallen into black holes. Instead of disappearing forever, everything consumed by a black hole might be expelled through a white hole, emerging into another region of the cosmos, or perhaps even a completely different universe. This would mean that black holes do not simply destroy, they transport. Every star, planet, and particle that has ever been pulled into a black hole might still exist, waiting to be released through a white hole somewhere on the other side. But this raises an unsettling question. What would happen to anything that makes the journey? The gravitational forces inside a black hole are beyond comprehension, stretching and tearing matter apart in a process known as spaghettification. Even if black holes and white holes are connected, is it possible for anything to survive the trip? Would matter emerge intact, or would it be broken down into its most fundamental components, reassembled only as radiation on the other side? Could a conscious being, something alive, pass through such a tunnel? Or would the forces at play make such a passage nothing more than a theoretical curiosity, forever beyond the reach of practical use? If wormholes do exist, they are likely to be highly unstable. The extreme conditions required to hold such a tunnel open would demand a kind of energy that is not known to exist in nature. Negative energy, an exotic form of matter that repels instead of attracts. Without this, any wormhole would collapse instantly, sealing shut before anything could pass through. Some theories suggest that certain unknown quantum effects might stabilize them, but until such effects are observed, the idea remains speculative. One of the most bizarre possibilities is that our universe itself might be the result of a white hole explosion. If white holes expel matter, then the Big Bang, the event that created all of known existence, could have been the ultimate white hole, releasing energy and mass into space in an instant of incomprehensible expansion. If this is true, then every black hole in the universe could be seeding new universes, each hidden behind an event horizon, each emerging from a white hole in a separate reality. This would mean that black holes are not just destructive entities, but cosmic wombs, birthing new worlds beyond our perception. This theory ties into the larger idea of the multiverse, the possibility that our reality is not the only one, but part of a vast collection of parallel universes, each governed by its own physical laws. If every black hole creates a new universe, then the cosmos is not a singular entity, but an ever-growing network of realities, endlessly spawning new dimensions beyond our reach. This would mean that the death of a star in our universe could be the birth of a universe elsewhere, that every collapsed giant is not an ending, but a beginning. And yet, despite the elegance of these ideas, white holes remain purely theoretical. No telescope has ever detected one. No experiment has ever confirmed their existence. If they are out there, they are either rare beyond measure, hidden in ways we cannot yet perceive, or so brief in their lifespans that they vanish before they can be recorded. It is also possible that white holes do not exist in the way we expect, that they manifest not as singular objects in space, but as events, moments where the laws of physics briefly reverse before normality resumes. Some theories even suggest that white holes are not visible because they exist outside of time as we understand it. If a black hole traps everything inside, bending time to an extreme where moments stretch to infinity, then a white hole might be the opposite, a place where time itself reverses, where everything that enters is instantly ejected not just across space, but into another moment in history, or even into a different version of time itself. If this is true, then the reason we do not see white holes may be because they are not bound by the same rules of existence that govern everything else. If black holes are the universe's great mysteries, then white holes are its greatest contradictions. They challenge the fundamental nature of what we believe to be possible, suggesting that space is not fixed, that time is not linear, and that the cosmos may be far stranger than we ever imagined. They force us to consider the possibility that destruction is never truly final, that what is lost may not be gone, but simply relocated, waiting to emerge in another form, in another place, or even in another reality. This brings us to the next great question. If black holes, white holes, and wormholes are all linked by the strange bending of space-time, then what does this say about time itself? One of the strangest consequences of extreme gravity is that it does not just warp space. It stretches time, slowing it down in ways that seem impossible. If the effects of gravity near a black hole can slow time to an infinite degree, then could black holes be more than just cosmic prisons? Could they be, in a very real sense, natural time machines? To understand this, we must explore one of the most eerie consequences of black hole physics, the slowing and warping of time near their event horizons. If black holes truly alter the flow of time, then they are not just objects of destruction, but windows into the deepest nature of reality itself. And if time can be slowed, then could it be stopped? Could it be reversed? Could black holes hold the key to traveling through time itself? If black holes are more than just voids in space, if they distort not only the fabric of reality, but also the structure of time itself, then they may hold secrets far beyond what we currently understand. The strange forces at play around these cosmic giants do not merely stretch space, they stretch time, bending it, slowing it, and in some cases, nearly stopping it altogether. What does this mean for anything that falls toward them? What happens to time at the edge of an event horizon? And could black holes be more than destructive objects? Could they in some way be natural time machines? Time is often thought of as a constant, flowing from past to future at the same steady rate for everyone. But this is an illusion. Einstein's theory of relativity shattered this assumption, revealing that time is not separate from space, but part of the same interconnected fabric. Gravity, the force that shapes the cosmos, does not just pull on objects. It bends space-time itself. The stronger the gravitational field, the greater the distortion. And near a black hole, this effect reaches extreme levels, warping time in ways that are nearly impossible to comprehend. A person standing on Earth and another person orbiting a black hole would experience time differently. The one on Earth would age normally, experiencing seconds, minutes, and hours in the usual way. But the person near the black hole would not. To them, time would seem to pass normally from their perspective, but to an observer far away, their clock would appear to slow down. A single second near the event horizon could stretch into hours, days, or even centuries for someone watching from a distance. This effect, known as gravitational time dilation, is not just theoretical. It has been confirmed through experiments and observations of objects moving through strong gravitational fields. Satellites orbiting Earth experience this on a tiny scale. GPS systems must account for the slight differences in time experienced by satellites compared to clocks on the ground. But near a black hole, this effect is amplified beyond all recognition. The deeper one falls into its gravity, the slower time moves. If someone were to orbit just outside the event horizon, they could return to find that while only a few hours had passed for them, thousands or even millions of years might have passed for the rest of the universe. This raises unsettling possibilities. If a black hole is capable of slowing time to such an extreme degree, could it be used as a kind of natural time machine? Could someone, by orbiting close enough to its edge, effectively travel into the future of the universe? In a sense, yes. A person who spent a few hours in the immense gravitational pull of a black hole could return to find that ages had passed outside. Civilizations could have risen and fallen, the stars could have shifted, and the very structure of the galaxy could have changed, all while they experienced only a brief moment. But there is a limit. The closer one gets to the event horizon, the more extreme time dilation becomes. If someone were to attempt to hover just above it, time would stretch so much that from an external point of view, they would appear to slow down almost infinitely. To an outside observer, they would never fully reach the horizon, only move closer and closer, slowing more and more, fading into a frozen state just before disappearing from view. For the person falling in, however, time would continue as usual from their perspective. There would be no noticeable change. They would fall toward the singularity, experiencing time normally until they were stretched and torn apart by the black hole's gravity. This paradox, where time slows infinitely for an external observer but continues normally for the person falling in, is one of the strangest implications of relativity. If black holes stretch time, then what does this mean for the universe itself? Could the structure of spacetime be shaped by these gravitational anomalies in ways we do not yet understand? Some physicists propose that black holes may not only slow time, but could be connected to distant points in the universe or even other timelines. If a black hole's immense gravity slows time to near standstill, then could it serve as a kind of cosmic time vault, preserving information or even matter indefinitely? There are theories that suggest the very nature of time could be different inside a black hole. If the known universe operates with a past, present, and future, what happens when space-time is crushed to a singularity? Some propose that time itself may cease to function inside a black hole in any meaningful way. Instead of flowing forward, time could become another spatial dimension, meaning that for anything trapped inside, there is no movement through time at all. Everything that has ever fallen in could still exist, frozen in an eternal state, never truly disappearing, but never able to escape either. Others suggest that time may not only slow, but reverse near a black hole under certain conditions. If black holes and white holes are connected, then matter that falls in could emerge elsewhere, not only in space, but in an entirely different time. This raises an even stranger possibility. Could black holes be linked to the past and future in ways we cannot yet detect? Could they be tunnels not just through space, but through time itself? If this is true, then black holes could serve as the ultimate time gates, places where the flow of time is disrupted to such an extent that the normal order of events is no longer guaranteed. But for now, this remains speculative. What is certain is that black holes have an undeniable effect on the passage of time. The deeper one falls into their gravity, the more the laws of time itself begin to break down. The implications of this extend beyond theoretical physics. If black holes can warp time, could they have influenced the history of the universe in ways we have yet to realize? Could entire regions of space be experiencing time at vastly different rates without us knowing? Could some civilizations in the distant cosmos be living in a slowed version of reality, experiencing a fraction of the universe's age while billions of years pass elsewhere? These questions remain unanswered, but one thing is clear. Black holes are not merely objects. They are distortions of reality, reshaping the fundamental nature of time and space. They are places where the normal rules of existence break down, where time is no longer a fixed progression, but a flexible, malleable force. If black holes distort time, then what does this mean for the fate of everything that enters them? If time stretches infinitely at the event horizon, then what truly happens to anything that crosses it? Is it lost forever? Or is it preserved in some unknown way, trapped in an eternal limbo? The deeper we go into understanding black holes, the more we encounter paradoxes that shake the foundation of physics. And yet, if black holes have the power to slow time, to freeze moments, to bend reality itself, then they may also hold the key to something even more profound. Because if time can be slowed near a black hole, then what happens when a black hole dies? Could the remnants of time itself escape? Could information, once thought to be lost, be released back into the universe in the final moments of a black hole's existence? This brings us to another mystery: Hawking radiation. The theory that black holes, despite their immense gravity, may not be eternal after all. Instead, they may slowly evaporate, releasing energy back into space over unimaginable timescales. If this is true, then even time itself may not be safe within a black hole. The process by which black holes fade away is one of the strangest and most debated ideas in physics, and it leads to yet another paradox. If black holes can die, then what happens to everything they have consumed? Does the information inside them disappear forever, or does it somehow escape? The next stage of our journey takes us into the heart of this mystery. If black holes truly evaporate, then their grip on time may not be as permanent as we once believed. And if they can fade, then perhaps they are not as final as they seem. Hawking radiation suggests that nothing lasts forever, not even the most powerful objects in the universe. But does this mean that black holes eventually release their secrets, or does their death create even deeper mysteries? The answers to these questions could change our understanding of the universe itself. If black holes are not eternal, if they slowly evaporate through Hawking radiation, then the universe does not allow them to last forever. But if they are not permanent, then what happens to everything they consume? If time stretches infinitely at the event horizon and nothing can escape, then does this mean that all the matter, energy, and information that has ever fallen into a black hole is gone forever? Or could it be that black holes do not simply store what they consume, but transport it somewhere else? The possibility that black holes serve as portals to other universes is one of the most radical ideas in physics. Yet it is not without reason. If black holes destroy everything that falls into them, then they would violate one of the most fundamental principles of physics, the conservation of information. This principle states that information cannot be lost, only transformed. If black holes do not destroy, but instead transfer information elsewhere, then they could be gateways, connecting different regions of spacetime or even different universes entirely. This idea arises from the same equations that describe black holes themselves. Einstein's theory of general relativity allows for solutions where space-time bends so extremely that it does not merely collapse into a singularity, but instead connects to another part of the cosmos. These solutions describe a structure known as a wormhole, a tunnel through space-time, where one entrance is a black hole and the other may be something entirely unknown. If such a structure exists, then a black hole might not be a dead end, but a passage, one that leads to an unseen part of the universe or an entirely new reality. A wormhole would function as a bridge, linking two separate locations in space and time. If the entrance of this bridge is a black hole, then anything falling into it would be carried through a warped tunnel of spacetime, emerging on the other side in a place beyond observation. This means that every black hole could have an exit point, a white hole, an event where matter is expelled rather than consumed. This raises an astonishing possibility. Could the matter being ejected from a white hole be the same matter that was once pulled into a black hole? If so, then everything consumed by black holes may not be lost at all, but simply relocated, transported through spacetime in a way that defies our conventional understanding of movement. This concept has led some to speculate that black holes may be responsible for the birth of entirely new universes. If a white hole exists on the other side of a black hole, then the matter and energy expelled might not simply reappear in our universe, but could form an entirely separate cosmos with its own laws of physics. Some theories even suggest that our own universe may have originated this way, that the Big Bang was, in fact, the eruption of matter from a white hole connected to a black hole in another reality. If true, then every black hole in our cosmos could be a seed, a gateway leading to the creation of new worlds beyond our perception. But even if wormholes exist, there is no guarantee they are stable. The immense forces inside a black hole stretch and tear apart everything that enters, warping space to such an extreme that anything attempting to travel through could be destroyed long before it reaches the other side. Some models suggest that exotic matter with negative energy might be required to hold a wormhole open. Without it, any such passage would collapse instantly, preventing anything from making the journey. If wormholes do exist, they may only be microscopic, forming and disappearing before they can be used in any meaningful way. Yet despite these obstacles, some physicists believe that the idea of black holes as cosmic tunnels remains one of the most promising explanations for the fate of information inside them. If black holes do not simply trap everything they consume, but instead lead to new regions of space, then they could be far more than just destructive entities. They could be cosmic connectors, shaping the structure of the universe in ways we are only beginning to explore. This raises even deeper questions about the nature of space-time itself. If wormholes are real, then space is not a rigid, fixed structure but a fluid one, capable of bending and forming tunnels between distant points. If black holes can open doorways, then could the universe itself be filled with hidden connections, pathways linking regions that seem, from an outside perspective, to be impossibly far apart? Could some galaxies, instead of being billions of light years away from one another, actually be connected through invisible bridges? Could the entire fabric of reality be shaped by an unseen network of space-time tunnels, allowing energy, matter, and perhaps even life to travel across vast distances in an instant? If this is true, then the very definition of distance becomes meaningless. 2 points separated by trillions of miles could, in reality, be only a short journey away through a hidden path in space-time. Black holes, instead of being cosmic endpoints, could be the entryways to these pathways, serving as the ultimate shortcuts through the cosmos. But if black holes do lead somewhere, then what lies on the other side? If falling into a black hole means traveling through a wormhole, then what would a traveler encounter upon exit? If white holes exist, then their outward eruption of matter would be unstoppable, pushing everything outward at incomprehensible speeds. If an object survived the journey through a wormhole, it might emerge into a chaotic environment, surrounded by energy blasts so intense that no normal matter could withstand them. Another possibility is that black holes do not lead to separate locations within our universe, but instead open into entirely different realms. If space-time is not a singular structure, but part of a vast network of parallel universes, then black holes could serve as bridges between them. This would mean that our reality is only one of many, that beyond every event horizon lies a separate cosmos, governed by different physical laws, where time flows differently and the forces of nature take on unfamiliar forms. If this is true, then black holes could be the key to understanding the multiverse, the idea that reality is not one universe but many, endlessly branching and expanding beyond what we can perceive. Every black hole in our cosmos could be a gateway leading to regions where stars burn at different temperatures, where gravity behaves in unexpected ways, where life might evolve under conditions unknown to us. But even if black holes do serve as portals, the journey would be one of unimaginable risk. The tidal forces inside them stretch and destroy anything that falls in, meaning that even if a wormhole exists, the process of entering it may be lethal. Some theories suggest that only information could make the trip, that physical objects would be torn apart before reaching the other side. If this is true, then black holes may be cosmic transmission devices, carrying data across the universe, but never allowing matter to survive the voyage. And yet, there is still another possibility. What if black holes do not lead anywhere at all? What if the idea of wormholes is a misunderstanding, and all that enters a black hole is simply erased from our universe, never to be seen again? If this is the case, then the question of what happens inside a black hole may be one of the deepest mysteries in physics, one that may never be solved. For now, wormholes remain hypothetical, their existence suggested by mathematics, but unconfirmed by observation. If they are real, they could revolutionize our understanding of space-time, opening possibilities for interstellar travel, time manipulation, and even journeys beyond our universe. If they are not, then black holes remain as they are now, silent, unyielding, consuming everything that crosses their event horizons without a trace. But whether black holes serve as cosmic gateways or not, their presence shapes the universe in profound ways. Some have existed since the beginning of time, relics of the early cosmos that may hold secrets to the universe's formation. These are not the collapsed remnants of stars, but something even stranger. Primordial black holes, objects that may have formed in the chaos of the Big Bang itself. If such black holes exist, they could provide clues to the earliest moments of the universe, answering questions that have remained unanswered for billions of years. If black holes are not just the collapsed remnants of stars, but potential gateways to other universes, then their significance stretches far beyond what we currently understand. But not all black holes were born from dying stars. Some may predate the formation of galaxies themselves, existing since the first moments after the Big Bang. These are the primordial black holes, ancient relics of the early universe, objects so mysterious and elusive that their very existence remains uncertain. If they are real, they could answer some of the biggest questions in physics, revealing secrets about dark matter, cosmic structure, and even the ultimate fate of the universe. Unlike stellar mass black holes, which form when massive stars collapse, primordial black holes would have emerged from the chaotic energy of the infant cosmos. In the first fraction of a second after the Big Bang, the universe was an unimaginably hot and dense sea of energy, filled with violent fluctuations. If certain regions of space had been compressed to extreme densities, those areas could have collapsed under their own gravity, forming tiny black holes instead of expanding outward like the rest of the universe. Unlike normal black holes, which require stars to form, these would have been born directly from the fundamental forces of nature itself. If primordial black holes exist, they would come in many sizes. Some might be as small as atoms, with masses equivalent to mountains. Others could be as large as planets. Because they formed in the early universe, they would have had billions of years to drift through space, hidden from view. Some could still be wandering undetected between the stars, remnants of a time before galaxies, planets, and even atoms had fully formed. One of the most intriguing possibilities is that primordial black holes could make up some or even all of the universe's dark matter. Dark matter is the invisible substance that makes up most of the mass in the cosmos, yet it has never been directly observed. It does not emit light. It does not interact with normal matter in any familiar way, but its gravitational influence can be seen on galaxies and large-scale cosmic structures. If primordial black holes are widespread, they could provide an explanation for this missing mass. Unlike other dark matter candidates, which assume an entirely new type of particle, primordial black holes would simply be objects we already understand, just on a scale we have never detected. Detecting primordial black holes is challenging because they do not emit light. The only way to find them is by observing their gravitational effects. Some scientists believe that if small black holes are scattered throughout space, they might occasionally pass in front of distant stars, bending the light around them in a process called gravitational lensing. If such an event were observed, it could provide direct evidence of their existence. However, despite extensive searches, no conclusive proof has yet been found. If primordial black holes exist, they could also play a role in the formation of galaxies. Modern astrophysics suggests that supermassive black holes sit at the centers of nearly every large galaxy, including the Milky Way. But how did these giants form? One possibility is that they grew from much smaller black holes, perhaps primordial ones. If the early universe contained a population of small black holes, some of them might have merged over time, eventually growing into the colossal objects that now anchor galaxies. If this is true, then primordial black holes are not just ancient relics, but fundamental building blocks of the cosmos. The question of whether primordial black holes are still active today is another mystery. If they formed with small masses, some might have already evaporated through Hawking radiation, disappearing entirely. But if larger ones still exist, they could be lurking in the dark spaces between stars, invisible until they interact with something detectable. Some researchers have even suggested that a primordial black hole might be hiding within our own solar system, possibly explaining strange gravitational anomalies observed in the orbits of distant objects. If such a black hole exists, it would be no larger than